Hey Math 2B, this video is part of a small series of review videos from Chapter 4. One of the topics in Chapter 4 was special right triangles. And basically we found out that there were two special case triangles in which we know the angles and we can establish the ratios of the sides just based on the angles. So one of them was a 30, 60, 90. And if you recall in class, we developed this by, here's a line of reasoning. And I'm just going to go through the reasoning, and then I'm going to give you kind of the brief summary of how we use this information. But I think it's important to really know where this comes from. It's not magic. So we started by considering an equilateral triangle. And of course, in an equilateral triangle, all three sides are congruent to each other. And if a triangle is equilateral, it's also equiangular. So we have three 60-degree angles. And all that I'm going to claim right now is that I'm going to draw the bisector of this bottom segment. So I'm just going to sketch it, but somewhere in here there is a segment that says bisect an angle, or bisect this segment. I'm just going to draw the line from the middle up to the top, and it looks like I didn't quite get the middle. I hope that you can just go with that. My assertion is that I have truly drawn the bisector, that this piece is now congruent to this piece because this segment right here is a bisector. Now, not a bisector of the angle up above, just a bisector of that segment. Now, with me just claiming that that is a segment bisector, and we've established it is possible to bisect any segment, I'm going to now use one of our ways of establishing two triangles are congruent, and that was side angle side. So if you consider the following, I've got these pair of sides that I've marked congruent down below that are marked in green. Those are congruent to each other. I also have this congruent angle right here that's 60 degrees. It's important that this angle be in between the pairs of congruent sides. So that's the angle that's congruent. And the other thing that I have is this pair of congruent sides. These are congruent, of course, because it was an equilateral triangle. So that's the other bit of side angle side. So with that, this establishes that this triangle, these two triangles, the one on the left and the right, really are congruent to each other, and they're congruent because of side angle side. Because of that, I can now assert that this angle must be a 30-degree angle. And if I've got a 30-degree angle and a 60-degree angle, the third and final angle has to be a 90-degree angle because of the triangle angle sum theorem. So this is 90 degrees. It's a little redundant to write that. But you can see this is the 30, 60, 90. Now, with just a little bit of reasoning here, if I assume that the longest side, or the sides of all the original triangles, are 2x in length, because I bisected this bottom, I know that this bottom one has to be x units long. So I've got 2x and x. And I can find the length of the longer leg by using the Pythagorean theorem. So I'm going to assume that I'm going to label it smiley face. So using the Pythagorean theorem, of course, a leg, in this case smiley squared, plus the other leg, x squared, is equal to the length of the hypotenuse, x, or 2x rather, squared. Now if I take and I square 2x, be careful, it's two terms there, so I've got two copies of that factor of 2x, so 2x times 2x, and on the other side that still equals x squared, and there's still a plus smiley squared. 2x times 2x is, 2 times 2 is 4x squared, and that's equal to smiley squared plus x squared. I'm going to take away one of the x squareds. I'm going to take away the one that's on the left-hand side. So on the right-hand side, I have 4x squared. I'm going to remove one of them. That will leave me with 3x squared, and that is equal to smiley squared. If I take the square root, principal root of both sides, I get that smiley is equal to the square root of 3x squared. And of course, x squared is a perfect square. Oops. So if I take the square root of x squared, I just get an x, so that can come out front. So this is x times the square root of 3. This is the length of the longer leg. So I can go ahead and now replace this with x times the square root of 3. So just for example, if I was to take and say, hey, if this longer leg was 10 units long, if it was 10, the if the hypotenuse was 10, if the hypotenuse was 10 units long, this short leg right here would have to be 5 units long, and the longer leg would have to be 5 times the square root of 3 units long. So this is summarized by this diagram, right? In a 30, 60, 90 triangle, if the shorter leg is length x, if it's x units long, sorry about that, if the shorter leg is x units long, then the hypotenuse would be twice that, it would be 2x, and the longer leg is not x. The longer leg is x times the square root of 3. X times the square root of 3. So let's look at just one example that uses this ratio, right? And I hope you have this in your notes, but I'm thinking short leg x, hypotenuse 2x, longer leg x root 3. So this is one of the problems that I've given you for classwork today while I'm gone and you have a sub. If you can see right here, if I think about these parts, right, the shorter leg is right here, it's x. The longer leg would be, or the hypotenuse would be twice that, it would be 2x. And the longer leg would be x times the square root of 3. So if I know that x is equal to this side, x is the square root of 3, that means that u, right, the hypotenuse, would have to be 2 times the square root of 3. And if x is the square root of 3, right, then the longer leg would be what x is, which is, let me move this down a little bit, which is the square root of 3, that's what x is, times another square root of 3. And if I multiply the square root of 3 times the square root of 3, I get that b would have to equal root 3 times root 3, which is root 9, and the square root of 9 is 3. So my values are u is equal to the length to root 3, and v is equal to 3. The other special right triangle we had was the 45, 45, 90. And basically, my justification for this is, think about a square. If you have a square, of course, you have 4 right angles, and you have 4 congruent sides. So I'm just going to take this, and I'm going to go ahead and draw the diagonal from this side to the opposite side. I'm going to do my best without a ruler. And when I draw that diagonal, what I do, because over here I do have a square, a right angle, and I also have congruent sides, I'm getting that these two triangles are congruent again by side angle side. Since they're congruent to each other, I know that these angles have to split the 90, so this has to be a 45-degree angle, and this has to be a 45-degree angle. If I decide that each leg was x units long, again, I'll introduce Smiley here. We'll figure out how long the hypotenuse has to be. Well, x squared, a leg squared, plus the other leg squared, is equal to the hypotenuse squared. So you can see on one side I've got 2x squared, 2 of them, right? There's one x squared and another x squared, and that equals Smiley squared. If I take the square root of both sides, I get the square root of 2x squared. It's the principal root is what Smiley is. And if I simplify that, because x squared is a perfect square, I get x times the square root of 2. So my hypotenuse here is equal to x times the square root of 2. This information is summarized with the following diagram in a 45, 45, 90 degree triangle. If a leg length is x, then the other leg would also have to be x, right? Because it's isosceles. And the length of the hypotenuse would have to be x times the square root of 2. So let's look at a couple examples of this. In number 5, we have a 45, 45, 90. And again, we were saying that if the legs are x units long, the hypotenuse is x times the square root of 2, which makes this pretty easy to figure out what x has to be, right? If x times the square root of 2 is equal to 3 times the square root of 2, that means that x has to equal 3. So in number 5, we have x is 3. And that means, of course, that both A would be 3 units long and B would be 3 units long. Let's look at one more. Let's look at example number 7. Again, if I say that the legs are each x units long, then the hypotenuse would be x times the square root of 2. So if this is my x, and I want to figure out how long the hypotenuse is, I need to take this particular value of x, right? And I need to multiply it by another root 2. So I'm going to take this 5 times the square root of 2 over 2, and I'm going to multiply that by a root 2. I'm going to write it as root 2 over 1 because that's clearly the same, and then I can kind of see that it's a fraction. In my numerators, I have 5 times the square root of 2 times the square root of 2. And in my denominator, I have a 2. When I multiply root 2 times root 2, I get the square root of 4, which is 2. This is just 5 times 2 over 2. I have a common factor of 2. So I end up getting that x has to equal 5. So if, not x is 5, I'm sorry, what has to equal 5 is, that's actually what x times the square root of 2 is. X times the square root of 2 is 5. So that means for this problem, m, the length of the hypotenuse, is 5 units long. And this other n value, right, has to be the same as the other leg. So it would be 5 times the square root of 2 over 2. So there's 12 of these problems that I would like you to finish. And I know that within the class, there's more than enough of you that are going to be able to comprehend and explain this to fellow classmates, so that you should all do a really good job and get this turned in by the end of the period.